In this lesson, we're going to look at inheritance patterns and pedigrees. Here's an example of a pedigree showing 3 generations of a family. We often number them with Roman numerals, so the generation goes horizontally, and this is generation 1, 2, and 3. And we often number the individuals like this as well. So for example, if I wanted to indicate this person over here on the right, this person is individual 2-6, generation 2, individual 6. The females are indicated with circles, the males with squares, and this horizontal line indicates a relationship that produced children. So person 2-2, 2-3, and 2-5 are all the offspring of this couple. When we have a condition that we are trying to track, we often show that by shading in the people who are affected by that. So this person might be affected by the condition, as is this person. And people who've died are often shown with a cross through them like that. So that's what a pedigree looks like. We're going to look at 3 different patterns of inheritance: autosomal dominant, autosomal recessive, and X-linked recessive. And as we look at them, you'll notice that the things to look for in a pedigree to figure out which of the 3 it is to ask yourself, does every affected individual have an affected parent? That's going to give us a clue. Is the condition present in every generation, or does it skip generations? Does the condition affect males and females approximately equally, or do we see, for example, more males affected? And is there male-to-male transmission? In other words, can a father give the condition to his son? Looking at these together will help us figure out which of the 3 it is. Let's first look at autosomal dominant. An example of a condition in humans that's transmitted with an autosomal dominant pattern is Huntington's disease. This is a neurological condition that causes movement disorders and dementia starting in middle age. Now, this is the same pedigree, but we're going to color it in differently. So let's say this individual is affected, and this daughter, and this son, and we'll color in a few more over here. This might be a typical pattern of autosomal dominant. Now, autosomal, remember, means that we're not talking about the sex chromosomes, we're talking about one of the other 22 pairs of human chromosomes. Here we see every affected individual has an affected parent. So if we look at this person, they're affected, they have an affected parent, and so on. We also see that both males and females are affected, and affected more or less equally. Yes, I've shown more males than females being affected here, but that's just due to chance in a relatively small pedigree. We also see male-to-male transmission occurring, so this father has given the condition to his son. So male-to-male transmission occurs. These are all features that we see in an autosomal dominant pedigree. Now let's add in some genotypes. I'm going to use capital H to indicate the dominant allele that confers Huntington's, and we know that this person must have one of those at least, and we know that all of these people must as well. Now, if we look at generation 1, this person doesn't have Huntington, so they must be homozygous recessive. And because this couple has a child that doesn't have Huntington's, this person must be a heterozygote. This person is homozygous recessive, and because their partner is also unaffected, they must be homozygous recessive, and therefore they can't transmit the allele or Huntington's disease to their offspring. We can similarly work out that all of these individuals must be heterozygotes. This individual is homozygous recessive, as is this, and so we can go from there. And all of these kids are homozygous recessive as well. So you can see that using a little bit of logic, we can work out what all of the genotypes are. So this is an autosomal dominant pattern of inheritance. Next, let's look at autosomal recessive. Examples of conditions in humans that are transmitted with an autosomal recessive pattern include cystic fibrosis, which is a condition that affects chloride channels and in particular affects the lungs and the pancreas, as well as a condition known as Tay-Sachs disease, which is most commonly prevalent in individuals of Eastern European Jewish background, or Ashkenazi Jews, and results in progressive neurological decline and death in infancy. So let's imagine this is a pedigree for cystic fibrosis. We might have an individual like this affected here, and let's say this individual is affected here, and this individual here. So we see affected individuals, but here the affected individuals do not always have an affected parent. Neither of these 2 individuals have an affected parent. We see that both male and females can be affected. And we also see that it's not present in every generation, and in fact it may skip generations. If we think of this in terms of alleles, and I'll put lowercase c for the alleles that confer cystic fibrosis, so these individuals must all be homozygous recessive because they have the condition, then we can work out that their parents here must have been heterozygotes because they themselves were not affected, so they're not homozygous recessive, but they must each have one of the recessive alleles that they can contribute. Similarly, over here, these parents must be heterozygotes. And we call individuals like this who carry the recessive allele but themselves are heterozygotes and are not affected, we call them carriers. And so you can see here that we've got two carriers who then have an affected child. So that's an autosomal recessive pattern of inheritance. Now let's look at X-linked recessive. So when we're talking about X-linked, we mean that the gene of interest is on the X chromosome. And remember that in humans, females have two X chromosomes and males have an X and a Y. And that makes a difference in how this is expressed in the phenotype. An affected male needs to only have one copy of the affected X chromosome because he doesn't have a second X chromosome. Whereas a female, if she has one copy of the affected X chromosome and one normal X chromosome, will just be a carrier but will not express the phenotype because she's got the dominant allele, which I haven't written here, but you could imagine, for example, a capital A here. She's got the dominant allele on the other X chromosome to compensate, which a male does not have. To be affected, a female would have to be homozygous on both of her X chromosomes, whereas the male only has one X chromosome, and if it's affected, he'll display the phenotype. So as a result, we see many more males than females affected in the case of X-linked recessive conditions, and often we'll see just exclusively males. We also see no male-to-male transmission. Fathers can't pass the condition on to their sons. If we think about two parents here with an affected father and a non-carrier mother, the father is going to give his affected X chromosome to all of his daughters. He gives his Y chromosome to his sons. And the mother is going to give one or the other of her X chromosomes to everybody. And so you can see that in this case, the affected father has all carrier daughters and no affected sons. In contrast, if we were to have a non-affected father and a carrier mother, the carrier mother gives her affected X chromosome to half of both her sons and her daughters, and she gives her other X chromosome to the other half of her sons and daughters, and the father contributes X chromosomes to the daughters and Y chromosomes to the sons. In this case, with a carrier mother and a non-affected father, you can see that half of the daughters are carriers and half of the sons are affected. And to end up with an affected female, you'd have to have a carrier mother and an affected father. Examples of X-linked recessive conditions in humans include Duchenne's muscular dystrophy, which is a progressive condition in which the muscle fibers degenerate, resulting in muscle weakness, and red-green color blindness, in which individuals have difficulty distinguishing red and green. Both of these are much more common in males than females. And because of the genetics like we've seen here, affected males are related to each other through female carriers. You can see here that this affected male came from a carrier mom, and this carrier mom could have had a carrier mom herself, that's where this one came from, or she might have been the daughter of an affected father, that's where these came from. So affected males are related to each other through female carriers. Let's take a look at what that looks like on a pedigree. Here we could have an affected man, and let's say there's an affected man down here as well. We know, therefore, that this person's genotype, if I use lowercase a for the recessive allele, is like this, as is this one. And this is a carrier female, therefore, so her genotype must be like this. This is an unaffected male, and we might imagine that their offspring are something like a non-carrier female, maybe this one's a carrier female. There's a 50% chance of each, and we've got a 50-50 chance of affected and unaffected males. So we just happen to have 4 offspring, 2 of each here. It wouldn't work out this perfectly, it's a probabilistic thing, but just to illustrate. So that's X-linked recessive inheritance, and earlier we saw autosomal dominant and autosomal recessive inheritance.